Starting our course, our lecture. No questions? Everything is clear? No worries? Okay, good. That's good. If you have any questions, do not hesitate to ask. Yeah? Not good?
You don't know. Maybe good, maybe not.
Maybe not. But if you understand that, it means good. If you have any questions, any part of misunderstanding or anything vague, please ask. The class is in person because of that, because you could ask questions, we could have discussions.
Sometimes you don't ask, maybe you understand everything.
Sometimes
You don't understand
anything. So if you don't understand anything, start from the beginning. Don't keep it to be accumulated. You just need to ask as many as questions you can. The questions are good. But some of you are shy. Or maybe you are thinking that if I ask this question, it means that I haven't listened to the lecture and it is not good. No, you ask. So if it is very basic, then I might say, okay, if you want this, we can talk for after the class, not in the class, because everybody knows that. But ask questions as much as you can. So what we do now, we go to edge trigger. Remember, we talked about master-slave, the latch, and we told you that it is good. It solves the problem of transparency, but still it is some kind of level. If during the level the data changes, then it won't be good. Now we okay. So let's do it late. Yeah, make it less. Yeah, better. Good. Okay. Now we have built a design that I am claiming that this is edge triggered. Very important. Edge triggered. It means that if we have an edge, if this is the clock, then with the edge, I mean, for example, if it is rising edge here, at this time, it works. And it doesn't work during the level. Either it is 1 or 0 or anything. So it doesn't do anything here or here, just at the edge. This is what we built. So let's see how it works. Last time I showed you the circuit, but now it is good if you go through the detail. So let's start with D, Q, and C. All of them are 0. Okay, so how do I write it to become pretty? Maybe I do it like that. So I start with black. So D is 0. I hope I can write it. D is 0. Clock is 0, and Q is also 0. We are at the state of 0. So Q bar is 1, so this is 1, this is 0, so this is D, and clock is 0, so clock is 0, and this is 0 also, and this is 0, so it is 1, and 1 and 0 is 1, 1, this is 1, we have 1 and 0 is 1. We have 1 here, coming here, 1. So we have 1 here. 0 there, 0 there. So what about up? So here we have 1. So this is also 1. And we have 0 here, so this is 1. This is 1. So this is 1 also, which is not important. But this is 1, so this is 0. And this is 0. Okay, everything is written. Okay. Anything missing? So this is the initial state. You see, Q is 0. We are at the state of Q is 0, and we don't have clock. Data is 0. Data was 0 sometime that it made the Q to become 0. Now we go to the, okay, this is what we have written. Now we go for D gets 1. D gets 1. And if, the clock is 0, so in either, even in the master slave, we didn't expect that it goes through all the way. But in the master slave, it could go through one step, which we talked like before. But now here clock is D is 1. Okay, so let's go to D is 1. Which color do I use for that? Let me see. Okay, no, orange. D is 1. Now D gets 1. D gets 1, so it is 1 and 1, so it becomes 0. Oh, I put it this side. This side. Why it's not writing? 1. So 1 and 1 is 0. 0 comes here. And 0 comes here. We have 1 at the output, so it doesn't change. Clock is still 0. And we have 0 here, so 0 comes here. 0 comes here and makes it 1. So this becomes 1. And 1 is here, so it still remain at 1. So 1 is here also. 1, 1, 1. It is 1. Okay, finish. And you see, Q is still 0. D gets 1. Q is still 0. That's something that we could accept from even in the master slave. But the beauty would be the next stage. In the next stage, we are going, so the Q bar is 1 and Q is 0, still Q is 0. 1 and 0 is still 1 here. We have 1 here, 1, okay, and 1, okay. Okay, this is complicated. Let me remove those things. Keep. I remove these things. Too complicated. I just want to keep whatever we have written now, which is this one. Remove. What did I remove? Too bad. So I don't want this. I don't want this. I don't want data is 0 and then 1. Oh, not this one. So where are these things? This. We don't need the red one, yeah? So I should get rid of red. Red. Oh, okay, now it's good. But I lost the black one also. The black one also. Too bad. Okay, it's okay. So now D is 1 and Q is still 0, and then we go to the next state, which is this. C becomes 1. Now C becomes 1. Let's see what happens. I put it with which color? Okay. Green, but I erased it, so it doesn't matter whatever I use. So I use green here. So clock is 1 now. Clock is 1. D is 1. So when clock is 1, we have 1 here, and still we have 1 there, and this is 1, this is 1, this is 0. So 0 is here, 1 is there. So everything is good up to now. This is 1, so now we have 1 here. We have 1 here. 1 and 1, it becomes 0. And this 0 make Q as 1. Okay? 0, NAND something is 1. And this one makes Q as 0. You see, when the clock gets 1, the data propagates to the output, and Q becomes 1. That's good. That's something that we wanted. Let me put the other things also. So this is 1. This is 0. So this is 0 also. 0. What else do we have? This is 0 also. And this is 0. 0 is still 0. Okay, good. Now let's go to the next move. Yes? When I write it, you could see. How do I make sure that you could see? You could follow. Huh? When I write, you know. Yeah. Okay. Maybe if it was in the blackboard, it was maybe better. I try to make it clear. Let's try. Now, what do? We make D0. In the previous design, when D becomes 0 and clock is still 1, it could propagate inside. And maybe then if clock becomes 0, then it goes out, which was not good. We are talking about this problem now. We are trying to solve this problem, that when the clock is still 1 and in the middle of the clock cycle the data changes, we don't want it to propagate to output. And we see how. So D becomes 0. Now D becomes 0. So how I try to come from bottom to up to see if you could follow. So I use red. D becomes 0, okay? D becomes 0. When D becomes 0 and clock is still 1. Why didn't we write 1 before? Because clock was 1. Clock is 1. Clock is 1, D becomes 0. When D becomes 0, the NAND at here it becomes 1. Okay? Because did you follow? It's hard. So the NAND, this NAND becomes 1 because one of the inputs are 0. And then the output of NAND is 1, so it comes up here. So this is 1 also. The 1 connected there. And now we have 1 here, so we have, this one goes to the NAND at the top. This one goes to the NAND at the top. That is 1, and the clock is 1. Clock is connected to 2 NANDs, one at the top bottom, the other at the middle. This is clock. So clock is 1. So 1 and 1. So the output would be 0. And 0 is 0. 0 comes up. And the NAND gate, 1 and 0, becomes 0, the NAND. And this is 0 also. The output of the NAND is 0. So still we have clock Q, because this is 0. Here we have 0, 0, NAND, something becomes 1. And this 1 also coming here. We have 1 at the bottom. We have 1 here. And Q bar is still 0. So you see, D is 0, but nothing changed in the Q. It doesn't change. Even if the clock becomes 0. Let's make the clock 0. Let's make the clock 0 to see if it changes. It doesn't change, and that's good. That's something that we built now, because in the previous design, when clock is 1, it goes half of the way, and then when the clock is 0, it goes to the output. But now it doesn't. I can show you that it doesn't. Now clock becomes 0. Clock becomes 0. We write it with, what do we write? Blue. Blue is good. Blue. So clock is 1. Clock becomes 0. Clock becomes 0. So we have 0 here, so it is 0 clock. So I first put the clock into these two NAND gates. So it is 0, so one of the NAND is 0, so the output would be 1 for the both of these NANDs, this and this. These two NANDs, the output would be 1. And this one coming to the NAND at the bottom. So we have 1 and 0. The output is still 1. This one goes to the NAND up. So this is 1 still. And this goes to the one here connected to that side also. So it's still 1. And what else do we have? We have 0 here, 0 here. So we have 1. And then we have 1 here. We have, because we have 1 here, 1 and 1 is still 0 here. So we have 0 here. 0 and 0 is 1. So it's complete. Still Q is 1. Q bar is 0. Okay? Still the same thing. So now what happened? Clock became 0. Now we give another edge. Another edge. We give it edge, a rising edge. Clock becomes 1. What do we expect? We expect that the data would appear at the output. What is data now? Data is 0. So Q is now 1. When clock becomes 1, it should appear at the output. So let's make the clock 1 with, what do I use? Orange, no, we have orange. Yellow is not good. So maybe purple. So clock is 1 now. Clock is 1. Since clock is 1, so I put first those two clocks. This is 1, and also the clock goes to the up gate. These two are clock. Okay? Please stare at it so you don't lose where do I write. So clock is 1. Let's see what would be changed. We had 1 here. We had 1 here, so still we have 1 here. We have 1, and clock is 1, and this is 1. So the output as this NAND gate becomes 0. You see, clock is 1. This one was 1. This one, and also this one was 1. So the output of this NAND becomes 0. When the output of this NAND becomes 0, the Q bar becomes 1. The Q bar becomes 1. When the Q bar becomes 1, we have 1 here. We also have 1 here, and we have 0 here. So we have 1 at this NAND gate, the output of this NAND gate. We have 1 and 1, Q becomes 0. You see what happened? What happened is this. When we have rising edge of clock, the data propagates. When we don't have rising edge, even if the clock is 1, Even if the clock is 1 getting low, nothing changed. Only when the clock gets 1, from 0 to 1, at that time we have the data coming out. Otherwise it doesn't go out. So if you look at the timing diagram, if I write a timing diagram, this is my clock. And let's say this is data, D. D, for example, is 0 here. Then at some times it becomes 1. Then at some times it becomes 0. And even during the clock cycle, it becomes 1. It still remains 1. Then here becomes 0 and so on. So what happens for the Q? So let's look at Q with orange. So at the rising edge of the clock, we look at the data. Data D is 0 at this time. So Q becomes 0 now, 0 at this time. 0. 0, not 1. I put 1. Let's make it 0. So Q becomes 0 at this time. At this time with a very short delay, let's say here, becomes 0. Q becomes 0. Then we have clock going down, and at this time, again, we have a rising edge. If you have a rising edge at that time, look at D at that time. At this time, D is 1. So Q becomes 1 with a short delay. Becomes 1. You see, we didn't look at the data during this time, whatever it is. But at the rising edge of the clock, at this point, we look at data. And whatever data is at that time, it propagates to the output. And this, you see here, data becomes 0 here. Okay, there is no clock, so data becomes 1 again. Okay, no problem. But here is the rising edge of clock. So at this time we look at data, and data is 1 again. So this Q still becomes 1. So as Q, you see Q didn't become 0 in the middle, and that was the problem with the previous design. With the previous design, if in the middle of that the data changed, then it could propagate. But here, nothing happens. Again, we have rising edge of the clock here, and whatever data is, you look at data and then you find the Q. So we look at only the edges. Here is the rising edge. This is the timing value. Since we are here, I will tell you something which the slide is coming later. There is a timing, of course. Nothing is instantaneous. We have gates, we have electrons moving, so we have delay. I told you the delay is because of R, resistance, and C, capacitor. We have capacitance, we have resistance here. So we have delays. So if we have delays, nothing is instantaneous. And you see in the circuit, when data is here and clock comes, there are circuits that needs to change something, as we wrote here. So you could see, they could get the data and move it to the output. It takes time. And even because of that time that we need for these gates to work, we need, pay attention here, we need data to be present before the rising edge of the clock for a specific time, not instantaneous. So it is not good if you have data, for example, coming up here and also the rising edge of clock at the same time. It is not good. The data should be before the clock for a specific time. This time is called setup time. So every latch, every flip-flop has a setup time. Setup time means the time that the data should be stable before the edge of the clock. If you violate this setup time, for example, this example, D and clock coming together, then the data might not propagate well. It doesn't work, and that's not good. And again, because there are some kind of propagation after data coming down, you need to keep data after the clock also. Just, for example, if you have data here and don't bring it down very fast, it is not good again. You need to hold the data for a specific time. That time is called hold time. So setup time and hold time, they are very important timing parameters for a latch, for a flip-flop. It means that before the edge, you have to make the data stable for setup time, and after the edge, you have to keep the data for the hold time. So I will have the slide later, but since I put it here, I told you. Yes?
What could happen if the data turns off before the clock?
Don't know. Since you didn't respect the hold time, the data might change. Undetermined. It's undetermined for sure, but if you know the exact delay of the gates, you can find out what happens. But we don't go through that detail, so we say don't do it. The manufacturer of the gate, the manufacturer of the edge trigger D flip-flop says that this is setup time, this is hold time. You should respect that so you get the proper result. If you violate that, then the output is indeterminate. No, we cannot confirm, we cannot say that for sure this would be the output. Okay, so again I say transition occurs on the clock edge. Yes?
So how's this different from the master-slave flip-flop?
At that time I gave you something. Let me see if I have it. Latch, master, slave. Yeah, this one. What if input changes in the middle of clock? So we have a clock, and then the data, for example, before the clock going high, the data is 1. So when the clock becomes 1, this data coming to the middle, and then when clock goes down, data goes out. Okay, that was master slave. Now I am saying that if during the clock cycle the data change, data becomes 0 here at this time. So at this time you see clock is still 1. Since the clock is still 1, this master works because the clock is 1. So now 0 is moved here, not the one that we had at this time. 0 comes here, and then when the clock becomes 0, this 0 goes output, a Q becomes 0. But what we wanted, we somehow wanted, this is the typical object that we want at the rising, at the edge only change. And if something happened during the clock, it doesn't affect the output. we get the output only at the rising edge. Okay? And did I talk about, no, I didn't, I guess. Yeah, I talked about with the clock, if you have a clock, when I wanted to introduce the concept of the clock for the latch, I told you the clock is very good for synchronizing everything. You remember? And for that, it serves two purposes. One is that everything would change at the clock cycle, and the next one is that during the clock cycles, between the rising edge of the clock, whatever combinational logic you have, they can work, they have time, they have delays, they take times, they work, and then when the result is ready for the next rising edge, we get the result. But with this circuit, it doesn't happen. If something changes during the clock, because they are working, it takes time, it might affect the output, which is not good. Okay? So the problem with this design is this, that what if the input changes in the middle of the clock? This will propagate, and we don't want it. And because of that, we go to a falling edge, an edge-triggered flip-flop. Rising edge, I showed you. If you want to have a falling edge, you can have an inverter for the clock, so you would have a falling edge. Okay. Okay. Now we talked about sequential logic. What was the main characteristic of sequential logic? It has memory. The output doesn't depend only on the input. It has some kind of memory, some kind of state stored there. So the circuit has a state. So what about the beginning? We want to start working with the sequential circuit. What is the current state of that? Do you know? It has a state. It is sequential. It has a state. But we don't know. We are just going to start working. For example, plugging on, connecting power to the circuit. So what happens there? What is the state of the sequential circuit? What's that? We don't know. It could be anything because it has memory. So it has memory from the previous function that it had before. Now we turn the device on, it has something inside. Okay, so it is not good because when we start our circuit, we want to have a function that we want, and we know we want to do something like that. If it is not known the state, then we cannot use it. Therefore, another important thing, every sequential design needs some kind of initialization, some kind of resetting, some kind of presetting, either reset to make it 0 or either preset to make it 1. So we need that for a sequential circuit. Otherwise, we don't know the state at the beginning. Every sequential circuit needs an initialization. So now we are going to build a preset and a clear for our design. And our first design is asynchronous. I will tell you what do I mean by asynchronous. So how to initialize the circuit? This was the D flip-flop, the rising edge clock flip-flop. So how do we make a reset and or a clear or reset, they are the same, or a preset, a set or preset are the same. How do we do that? For example, if you want to make a reset, then reset means Q bar gets 1 and Q gets 0. How do we do that? It could be easy with this design. We can bring something here when we make it 1, When we make it 0, so this 0 goes to this NAND, and the output of the NAND becomes 1. So that's good. But it is not enough because it has some kind of feedback and so on. We have to connect this to different places. I will do it for you. So we do this. We connect this to the NAND gate here, the NAND gate here, and also we try to keep the data with this preset. Clear. We called it clear, and we called it active low. You remember when I told you when there is a bar here, it means that it is active low. It doesn't mean the complement of clear. It doesn't mean that. It means that the clear signal is active low. What does it mean? It means when it is low, it is active, it works. So when you make this 0, it clears. When you make it 1, it is not active, nothing happens. So when you make it 0, it clears the output. The output becomes 0 and Q bar becomes 1 with clear. We could do something similar for the presets. If we connect preset to here for the Q, and also we put it here to make it some kind of stable, then when I put it with blue, when preset becomes 0, it is active low again. You see the bar at the preset, it means active low. Again, I repeat, this doesn't mean there is a signal called pre, and this is the inverse of that, the complement of that. No, this is the signal of preset, which is active low. So when you make the preset 0 active low, so the Q becomes 1 and Q bar becomes 0. So with this that we have now, we can initialize our circuit. We start a circuit, for example, we want to start from Q 0. Q becomes 0. So we activate clear, we make it 0 clear, and then when it is initialized, then we make it back. The clear should be 1 for the regular operation, and the preset also should be 1 for the regular operation. But when we want to clear, we make it 0. When we want to preset, we make it 0, active low. But during the regular operation, they should be 1. They should be inactive. Okay? So we built a preset and clear. And you see, this doesn't depend on the clock. Regardless of the clock, when preset is active, Q becomes 1. When clear is active, Q becomes 0. Okay? So we call it asynchronous. They are asynchronous, not based on the clock. When something is changing based on the clock, then it is synchronous. But it is not synchronous, so it is asynchronous. We built asynchronous, preset, and clear. Okay? And this is the symbol. So you see, clear is active low. I told you if you put a circle at the beginning, it means active low, and it is good if we write this way. And preset is also active low, and this is the rising edge flip-flop, edge triggered rising edge flip-flop with clear and preset. So it's now complete. We have a very good sequential element called D flip-flop. The D flip-flop works on the rising edge of the clock, and it stores the data and puts it in Q. This is the basic element of sequential design. And timing diagram I showed you before. When there is clock edge, the data goes. If there is not, it goes. I can write the timing diagram with preset and clear also. So let's do it. How do we do that? We don't have space here. Just let me bring another slide so I write here. Okay, timing. We have clock. Okay. We have clock. This is clock. This is clear.
Sir?
Yes?
Can I ask a question?
Sure.
What if you put clear and preset on as one at the same time?
No, it's not. No, 0 at the same time. 1 is good. If you put 1 for both of them, they are good. But if you put 0, it's not good. It's not valid. You shouldn't do that. Sometimes, because of that, they just put one of them, either clear or either preset. But this is the complete design. You have all clear and you have preset also. You shouldn't do that.
So it's to set or Q or QR, or to...
If you put both clear and preset 0, then it is not stable because that becomes that 0. That 0 comes here, becomes it 1. This again becomes it 1. So it is not stable.
If you choose one or the other, or say you just choose clear, or you just choose...
Yeah. Either only clear becomes 0 or preset becomes 0, not both of them at the same time. If you do that, it will not get stable. So because the 0 of Q bar goes up and makes it 1. And that 1, but you made it 0 because of the gate, so it's not stable. So this is clear, for example. This is preset. It is 1. And this is data. D. For example, it is 0. Then it becomes 1. Then it becomes 0. Then it becomes 1. And then it becomes, let's say, 0 here. Okay. So this is, let's draw the timing diagram. And the clear, let's say clear becomes 0 at this time. And we have also Q. So at the beginning, we don't know the initial state, so we don't know the Q. But from the moment that we have a rising edge of clock and the data is 0 at this time, so Q becomes 0 at this time. Before that, we don't know. Q is either 0 or 1. It is the initial stage. It comes from the previous history, whatever it is. But here we are sure that when we have a rising edge of clock and the data is 0, so the Q, the data is 0, so the Q becomes 0. Why did I put 1? The Q becomes 0 because the data is 0. Q becomes 0. Then we have a rising edge of clock again here, and at that time data is 1, so Q becomes 1 here. Okay, but sometime later, in the middle of the clock, the clear becomes 0. As I told you, clear is asynchronous, and it works. As soon as it comes, it works. So clear became active. When clear is active, then Q becomes 0. So because of the clear, Q becomes 0, because we made it clear. Now you see, Q was 1, but clear came. When clear came, Q becomes 0. Again, we go, and then let's say that clear became 1 before the next rising edge. If it doesn't get 1, so as long as the clear is 0, the Q will be 0. It doesn't change. But let's say that it became 1 here, and in the next rising edge, the data is 0, so still data is 0. So we have 0 again. It was 0, it becomes 0. 0 again. For the next rising edge, again, for the next rising edge, the data is 0. So the data changed this time, but it didn't have any effect because it was during the clock cycle, and so etc. Now this is the output. Q became 0 when clear came, and at the rising edge, if the clear is 1, the rising edge works and the data goes out. Okay? This is the thing that I talked with you about setup time and hold time. You see, this is the clock. This is the clock. And this is data. Data, for example, is 0. At some time, it goes 1. And with the rising edge of the clock, we want the Q to become 1. We have 1, clock comes, so the Q becomes 1. To the circuit to work properly, you should have some time before the rising edge with where data is stable. So data should become 1 because here we want it to become 1. The data should become 1 at some time more than setup time before the rising edge of the clock. And after the rising edge of the clock, you should keep the data, you should hold it, you should keep the data to work properly. So these are the setup time and hold time. Setup time, hold time. If you make the data sooner, that's good. You respected setup time. You shouldn't do it later. So after this moment, if you change data, then it might not work, and the data going out. And even you have to hold it for this time. If you hold it more, that's good. You longer, you hold it. But if you hold it less, then it is not good. And the Q might not work, the Q might not be the things that you wanted to be. Okay? Yes?
During the raising of the clock or drawing, so what happened in the circuit?
During the rising edge?
Yeah.
We did that. The things that I put, this one. Where was that? This is what we have done. Okay, I guess after, oh, here. This is what we have done. You see, when the clock, here, clock, for example, became 0, and then clock become 1. I showed you what happens exactly inside. But from now on, you don't need to to look at the inside. You know that when clock goes up, with a delay, the data will propagate to Q, to output to Q. Do you want me to go through it again? No, it's hard. It's complicated. You should do it. Ina couldn't follow me when I tried to do it, so it is very complicated to follow what I suggest you do it for yourself. You do this for yourself to see what happens. Okay? Feda, yeah? Feda is okay? Correct? Feda, okay. Yeah, so you should practice yourself to see what happens. If you want to see what is happening inside, then you should use this. But for the outside, from now on, we just use this. It's very easy. When there is a rising edge, the data comes output. Data is 0 here, so output becomes 0. And this is the setup time and hold time. Oh, and also there is another parameter, timing, that you could find in the data sheet of the flip-flop. It's called clock to Q, DCQ. When the Q changes after the rising edge, it is not instantaneous. It has a delay. This is DCQ, clock to Q. The time from the clock to Q appears. So this is another thing that you could find in the data sheet of the flip-flop that you buy or you use. If you use Ultra, the board that you have, then you could see the specification that how much is the DCQ, how much is the setup time, and how much is the hold time. When you synthesize your circuit, after you build your circuit, when you synthesize, there is a report. It will give you the setup time, the hold time of the latches that you have in the design, the flip-flops that you have. So setup time and hold time, they are two important timings that you should follow to make it work. Now we will have a specific section for sequential components, the same as we did for combinational. You remember we had a section of RTL combinational components that I told you that we have a bag, the components are there, every component you can use it. We will talk about its functionality, its cascadability, its delay, timing. We talked about these things for them. The same thing we will do for the sequential components in the next section, but here, just since we have talked about flip-flops, D flip-flop, T flip-flop, JK flip-flop, just an application I will show you, but the detail will be coming later. So I would like to build a counter. So what do I mean by counter? We talked about the tally counter that we had before. We want something that could count with the clock cycle. When the clock comes, and ideally we would like it to be rising edge triggered, not level triggered. When the clock comes, it counts. If it is 2, it becomes 3. If it is 5, it becomes 6, and so on. It counts. So we would like to build a counter. The counter that we are building first is asynchronous. I will tell you why I call it asynchronous. I will use T flip-flop for my counter. You remember T flip-flop? This is the table that we would like for the counter. If we are in a state 0, then the next clock becomes 1. If we are in a state 1, the next clock comes, we want to output become 2. So it starts from 1, 2, 3, goes up to 15, and then the next clock becomes 0. Again, 0, 1, 2, 3. So this is the current state, the current Q of the circuit. When the clock comes, the next Q becomes this, and this is a counter. We start from 0, going up to 15 because we have 4 bits, and then again 0. This is a counter, okay? When we have this kind of circuit, we think that it should be a sequential circuit. So with working with a clock. And what do we use now? We use a T flip-flop. You remember T flip-flop. T flip-flop is a toggle flip-flop. When the input, the T, is 1 and clock comes, the Q toggles, becomes complemented. If it is 1, becomes 0. If it is 0, becomes 1. Okay? So how do we use that? Let's take a look at this table. If you look at this table, Q0 and Q0 plus. Look at these two columns. With every clock cycle, Q0 plus is the complement of Q0. You see? This is 0, it becomes 1. This is 1, it becomes 0. This is 0, it becomes 1. Okay? So, very simple. We can use a T flip-flop to build this. This is very simple. We just use a T flip-flop to build the Q0. The Q0. So, this is the Q0. And if I connect this to 1, because if T is 1, then with every rising edge of the clock, it toggles. That's good. So we built Q0. Okay? Good. Any comments? Everybody? Okay? Q0 is keep complemented with each clock cycle. 1 0 1 0 1 0 1 0 1 0 1 0 1 0. So we just use a T flip-flop and toggle it with every clock cycle. So Q0 is done. Now Q0 is done. Now let's go to Q1. Q1, look at the Q1 plus and Q1. Q1 plus is complemented at these positions. You see, when it keeps a state for one clock and then complements at the next clock cycle. You see 0 1 1 here 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1. This is the pattern of the Q1. So if we look at that, when it complements, when we have a transition of Q0 becoming 1, when Q0 becoming 1, Q1 complements, negated, toggles. Okay? When Q0 is 0, it doesn't change. It doesn't change. But when Q0 is 1, it changes. You see? Let me show you with red. When Q0 is 1, this complements. When Q0 is 1, this complements. But when Q0 is 0, it doesn't change. Okay? So what do you think? When Q0 is 1, it should toggle. When Q0 is not 1, it shouldn't change. What do you think? What to do? How to build this? What would be a good circuit for making Q1? Any idea? Any suggestion? Suggest? Why not? I am telling you, when Q0 becomes 1, it should toggle, and when it is not 1, it shouldn't toggle. So if, yes? Perfect, very good, of course, that's perfect. So if I connect Q0 to toggle off the next flip-flop. So this is Q0, this is Q1, this is Q2, this is Q3. So if I connect Q0 to toggle input of the next flip-flop, then when Q0 becomes 1, it toggles. So Q is also becomes 0. And when it is not 1, it doesn't. Okay? Good? Agree? Any objection? Overlooked. Okay. So the same thing, we will talk about it the same for Q2. So if you look at Q2, when Q2 is toggled, Q2 is toggled here. Q2 is toggled here. Q2 is toggled here. Q2 is toggled here. If you look at Q2, when does it toggle? When Q1 becomes 1. When Q1 becomes 1, it toggles. Yeah? You see, when Q1 becomes 1. So, no, here we have 1 also. So, what do we do? When Q1 becomes 1. When Q1 and Q0, both of them becomes 1. Yeah. When Q0 and Q1, both of them becomes 1, then we toggle it. So what do we do? Oh, I erased that one. So the first one was this. So the second one, we have the AND of these two. When they are both 1, it should toggle. Okay? Good? When both of them are 1, then it toggles. Here. Agree? So again, for the next one, if we look at the next one, when Q3 toggles, Q3 toggles here and here. When Q0, Q1 and Q2 are all 1, it should toggle. Otherwise, it shouldn't. So now we use the output of this AND gate, which is the AND of Q0 and Q1, and we AND it with this Q, and we give it to this toggle. Good? Done. Now we have built a counter. The clock comes. So let's see what happens when clock comes. The first clock comes. The first clock comes. I put it with blue. What happened? Okay. When the first clock comes, this one here is, we have a 1 here. So this should toggle. So Q, and we have started from 0, 0, 0, 0. So this Q becomes 1. This Q becomes 1, and yes, the clock come, and that's happened. And then for the next clock, the input of this is 1. So for the next clock, the Q bar, so let me write the first clock, 0, 1, 2, 3, 4, 5. So the first clock comes, Q0 becomes 1, and the rest, because the T at that time when the clock came, the T was 0 for those things. So they didn't change. But when the next clock comes, the Q is 1, so the input of T is 1, then it will toggle. And also the input of this flip-flop is 1, so this also toggles. But the other things, the output is, the toggle input was at the time of the clock, it was 0, so it doesn't change. The next clock comes. Do we have 1 here? Yes, we have 1 here, so this should toggle. No. Okay, we have 1 here, but we have 0 here. So 1 and 0. So the next one, it doesn't change it. So this one toggles for sure. The Q0 toggles. This one doesn't toggle because Q was 0 before, so it doesn't toggle, and this also toggle. Now we have 1 and 1 here, so the output of this AND gate becomes 1. The next clock, the Q2 2 toggles, and so on. Okay? A counter from 0 to 15, again 0 to 15, and so on. So this is the circuit. No, this is it's different. You know, it's not that it doesn't have the AND gate. No, it's not good. Don't look at this later. Oh, we could have done another thing. Okay, why didn't we do that? So that was the first thing that we have done, and with that design, actually we built a synchronous design, because at the rising edge the output goes. Sorry about that, I put the synchronous first. Now we want to build a synchronous circuit. Again, I repeat what I told you. When Q0 becomes 1, at that time we want Q1 toggles. So instead of that we have done that, we connect Q to the clock. If we connect the Q to the clock, then when Q becomes 1, it has a clock. And then we have 1 at the input of all of the T flip-flops. So it works. And then, again, I will give you the timing diagram of this. Again, we connect the Q of this to this clock, and Q of that to this clock, and see. So let's draw the timing diagram. So the clock, we have clock, we have Q0. So Q0 is 0 at the beginning. With we have falling edge. With the falling edge of the clock, it goes up I. So Q0 becomes 1. And this Q0 becomes the clock for this flip-flop. So this flip-flop doesn't have falling edge, so it doesn't change. But again, we have a falling edge of clock here, so Q0 toggles. Let me complete the Q0, and then we go for the other one. So Q0 toggles with the falling edge of the clock. Okay. Now, if you look at this, we connected Q0 to the clock of the next flip-flop. Where are the falling edge of this clock? The new clock. Here, here, and so at these positions, Q1 toggles. Q1 is 0, so here becomes 1. It is 0, here becomes 0. It is 1, and here becomes 1. See? Yeah? And this would be the clock for the next T flip-flop. So Q2 is 0 until the falling edge of its clock. And at this time, it gets high. So we have built a counter. You see here we have 0, 0, 0, 0. Then we have 0, 0, 0, 1. Then we have 0, 0, 1, 0. Then we have 0, 0, 1, 1. Then we have 0, 1, 0, 0. Then we have 0, 1, 0, 1. So we built a counter. Sorry about the mistake that was the synchronous one. So here we have asynchronous design. Why? Because I put it with highlights. Okay. When the clock have a falling edge of clock here, this Q becomes 1 with a delay, the delay that we talked. So there is a delay here for the Q0. Okay. And then later, when again we have a falling edge here, so we have a delay, a later time, this becomes 0. And when this becomes 0 with a delay, it is the clock for the next one, so this one has more delay, and it becomes 1 later. So the delay propagates. Q0 has 1 element of delay, Q1 has 2 delays, Q3 has 3 delays, and Q2 has 3 delays, and Q3 has 4 delays. And it means that with the clock, when we have clock, all of the outputs don't change at the same time, which means that it is not synchronous. Synchronicity means they change at the same time, even with a delay, a specific delay, but they change at the same time. This doesn't happen. So it is not synchronous. It is asynchronous counter. How do we make it synchronous? With the design that we are going to show you. For the synchronous, this is the thing that we have talked before. So this goes to T. This goes to T. This one and this one goes to T. But here, the clock is connected to all of them. So all of them have the same. Do you have questions? Questions? So clock goes to all of them. With the falling edge of the clock, the change appears at the output, and it is good. We have a synchronous counter that we built. With this design, another point. With this design, you could have a T flip-flop with rising edge or falling edge. It doesn't matter. Both of them work with this design. But this design only works with falling edge T flip-flops because the Q here should make a falling edge. Okay, you know? So with this design only works with the falling edge. But the other design works with either falling edge or rising edge of T flip-flop. And this is the design you see. The other thing that I could show you here in this design is, it's already gone. Oh, we didn't do the quiz. Too bad. The other thing is enable. Usually for our components, we talked about this in a combinational components, we would like to have some kind of enable. If it is enable, it works. If not, it doesn't work. It will help us for cascadability and these things that we talked before. So here we put an enable here. You see here, this enable. The first T flip-flop, we don't connect it to 1. Instead, we connect it to enable. If enable is 1, it counts. If enable is not 1, it doesn't count. So very simple. Just instead of 1 connecting to the first T flip-flop, we make it enable. If enable is 1, this works. This counts. If enable is not 1, then it doesn't work. Okay, that's it. Have a good weekend. When is the final exam? Do you know the time? 30th. July, 30th July. And the last day of the classes are 21st, 23rd. Okay, very good.